Welcome to the second lecture of this week in EE404. In the earlier lecture, we have seen the phase plane trajectories of linear systems when the eigenvalues of the A matrix are real. So in this lecture, we are going to try to see the complex eigenvalue case. So why do we see, or why do we examine these linear cases while the course is titled Nonlinear Control Systems? So in general, our ultimate aim is going to be investigating the trajectories or phase plane trajectories of nonlinear systems. But we have also a tool called linearization. When we look at the trajectories of a nonlinear systems, we are going to see that there will be equilibrium points in the phase plane. And we are going to see that the trajectories of a nonlinear system around its equilibrium points can be characterized using the linearized system trajectories around the same equilibrium point. So we are going to use these results or use these phase plane trajectories for linear systems in order to be able to obtain the approximate phase plane trajectories of nonlinear systems around the equilibrium points. So this is going to be quite important when we go into the topic of phase plane trajectories of nonlinear systems. So now let us consider case 2. Remember, case 1 was the real eigenvalue case, and in this case we are considering lambda 1 and lambda 2 are complex. Okay. Let us start with an example. I will try to develop the theory while I'm trying to solve this example here. The example is going to be as follows. So I have 0, 1, minus 5, minus 4, x, and the task is to draw the phase plane trajectories. So you might guess that this system, in this case the A matrix, is going to have complex eigenvalues. Let us first try to identify the eigenvalues and eigenvectors of the A matrix. In this case, I first calculate D of S, which is the determinant Si minus A, the characteristic polynomial of the system. Let us calculate the matrix Si minus A. It is going to be S plus 4, minus 1, and 5. And the determinant of this thing is going to give me the characteristic polynomial, S squared plus 4S plus 5. So we see that if I calculate the discriminant here, B squared minus 4AC, you see that it is going to be a negative one. That means that we will have complex eigenvalues here. So I can write this polynomial as follows: S plus 2 squared plus 1. Equating this to 0, I get the eigenvalues. Lambda 1, 2, or let us write lambda 1 is minus 2 plus j, and lambda 2 is equal to minus 2 minus j. Remember, we are always considering A matrices with real elements. That means that if I have a complex eigenvalue, then the other eigenvalue is going to be its complex conjugate. Real coefficient polynomials, if they have complex roots, then the conjugate of those roots are also roots of the same polynomial. So I have these eigenvalues. Let us try to identify the eigenvectors corresponding to these eigenvalues. In this case, I first calculate A minus lambda 1 identity. And this is going to be 0, 1, minus 5, minus 4, minus identity times the first eigenvalue. Okay, so I have minus 2 plus j, minus 2 plus j, and I have 0, 0 here. Well, that is going to be equal to, so I have the 2 minus j, negative of this eigenvalue, 1, and I have minus 5, and minus 4 plus 2, it's minus 2, and I have minus j. Okay? Now I have to find a non-zero vector in the null space of this matrix, A minus lambda 1 identity. That means that I need to find a non-zero vector, and when I multiply that non-zero vector with this matrix, then I need to get exactly zero vector. So I can make up a vector here. E1 can be, for example, it is 1 and the negative of this value, -2 plus j here. When I multiply E1 with that matrix, let us see what we get. A minus lambda 1 identity, E1, is equal to, so 1 times the first column, so I have 2 minus j and -5, plus the second element times the second column. So I have -2 plus j, and the other element is going to be -2 plus j, -2 minus j times -2 plus j, okay? The vector is given like that. So we see that here this +2 cancels this one and -j cancels this one. So I would get the result as 0, and I have -5. And you see that here I have -2 minus j, -2 plus j. This is going to be the magnitude square of this complex number, which is equal to 5. Okay? And that gives me 0, 0, as you see. So you see that this is my first eigenvector. Now I need to calculate the second eigenvector as well, but here I would like to show you something interesting to save you some effort. So here, this first eigenvector satisfies the following relationship. A times E1 is equal to lambda 1 times E1. Okay? And I know that lambda 2 is nothing but the complex conjugate of lambda 1. So here we see that lambda 2 is lambda 1 complex conjugate. Let us say that this bar just shows the complex conjugate of the complex number. I know that lambda 2 is the complex conjugate of lambda 1. Let me take the complex conjugate of both sides here. And remember that in complex numbers, complex conjugate operation can be distributed over complex number multiplication and addition, actually. But the addition will not be useful for us, but we can actually here distribute the complex conjugate operation over the individual multiplication elements here, all right? So if I take the complex conjugate of both sides, let us try to distribute the complex conjugation over the elements of the multiplication, lambda 1 conjugate, E1 conjugate. I know that A matrix is only composed of real elements. That means that complex conjugate of A is going to be itself, okay? And that means that we get the equation here, E1 bar. But I know that lambda 1 complex conjugate is nothing but lambda 2, okay? So I have A times E1 bar is equal to lambda 2 times E1 bar. So you see that this is the eigenvector equation for the second eigenvalue, and I see here that the corresponding eigenvector should be E1 conjugate, okay? So I see here that, so we really do not have to calculate. This is for lambda 1 equals to -2 plus j, and E2 is going to be just the complex conjugate of that first eigenvector, okay? 1 and -2 minus j here. For lambda 2 equals to -2 minus j, okay? That is pretty good. So we don't really have to make these calculations over in order to be able to calculate the eigenvector corresponding to the second eigenvalue, all right? So here I would like to again make a change of state vector, but here you see that the eigenvector is a complex vector, okay? If I define my state vector change in terms of the eigenvectors, then I might get some z variables which are actually which have complex elements. Okay, so I really do not want to now actually deal with these complex numbers here, and I don't want my new x's to be just these complex vectors. Okay, our original state space is z1 and z2, sorry, x1 and x2 here, our original state variables, and I would like to define vectors that I can visualize here as z1 and z2 here. But if I try to define my first vector, neo-coordinate axis, as this complex vector, then that is clearly not going to, it's not going to be possible to be able to for us to be able to visualize that vector in the real plane R2. Okay? That is why I really do not want to define my new coordinate axis out of these eigenvectors. Instead, we are going to do the following. So I will calculate real of the first eigenvector, which is going to be the real parts of the elements here, 1 and -2, and the imaginary part of the eigenvector. Okay? That is going to be 1 and 1. All right? Now we know that these real and imaginary parts of the eigenvector are actually real vectors, and I can visualize them in my state space. If I do that visualization here, let me try to show them to you. So I really do not need here. So this is my x1, this is x2. I would like to define my new coordinate axis out of this vector. Okay? It is 1 and -2. For x1 is equal to 1 and x2 is -2. So it is going to be a vector passing through the origin and this point here. Okay? So this is going to be my z1 axis, and the z2 axis is just going to be this. All right. So let me check my notes. I don't really remember. Yes, I know what mistake I made here. So I have calculated real of E1. It is 1 and -2. Imaginary of E1. Imaginary part of 1 is 0. So I'm making a big mistake here. Imaginary part of this thing is 0, and the imaginary part of this is 1. Okay? Now everything started to make sense. So here the first vector is again the same, but of course z2 is not this one, because the z2 axis is going to be defined out of that second vector, which is 0, 1, and we know that 0, 1 is going to be just this vector. Okay, and therefore my second z2 axis is going to be equal to the x2 axis. Okay, so I have z1 in that direction and z2 in that direction now. Now I would like to make a coordinate change, making my new coordinate axis this one and this vector and that vector. Okay. Now how can I do that? It is the same as before. We have already done this. So I have put the first vector into the first column of the P matrix and the second vector into the second column of the P matrix, which gives me the P matrix 1, -2 and 0, 1. Okay? Now let me try to invert this. Its inverse is also going to be useful. The determinant is 1, as you see. So the only thing that I have to do here is to change the elements on the main diagonal, 1, 1, and change the sign of the off-diagonal elements, 2, 0. This is the inverse. And I need to define my new z vector as P times, so P inverse times x, and x equals to P times z. That is our classical state variable change. So what we are trying to do is to write any x vector in terms of the columns of P. This equation tells me that, and here you see the inverse relationship. Okay. we know that such a state variable vector change gives us the following system. Since I have already done this a couple of times now, I can write this directly. P inverse AP Z, and that is A bar times Z. So our A bar, our new A matrix, is going to be here P inverse AP. Let us now try to calculate this new A bar matrix. Remember, when I put into the P matrix the eigenvectors as my column, new column vectors, then the A matrix, A bar matrix, turned out to be diagonal. Here, do you think this new vector, the first column of the P vector, do you think it's an eigenvector? That is my question. 1 minus 2. Do you think it's an eigenvector? So let us, checking it is quite easy. 1 minus 2, multiply that A matrix with 1 minus 2. So the A matrix is 0, 1, minus 5, minus 4, and 1 minus 2. It is going to be, I have minus 2 here, and I would have 8 minus 5, so it is just 3. So do you think this new vector is a constant multiple of this vector, 1 and minus 2? Clearly, I cannot write this minus 2 and 3 as a multiple of this vector here. So here I can say that this real E1 is not really an eigenvector of the matrix A. And the same thing is true for this one, unfortunately. Multiply this vector with the matrix, then it's going to give me the second column of that matrix. And you see that the second column is 1 minus 4, which is not a multiple of this vector. As a result, these vectors that I use as my new coordinate axis, they are not eigenvectors. So here, I really do not expect this A bar to be diagonal anymore. Okay? But the new form we are going to see is going to be useful in some other aspect. Let us calculate A bar. A bar is P inverse 1, 1, 2, 0 times A. A is 0, 1, minus 5, minus 4. And I have P itself, 1, 1, minus 2, 0. So if I do this multiplication, I have the P inverse still here. And let us do this multiplication instead. So I have here, I would have the minus 2 here in the first element, and I would have here 8, and the second column 1 and minus 4. Let us do this multiplication as well. The first row is going to be minus 2, 1, and the second row is going to be 8. I would have here minus 4, and that would give me. No, this is actually wrong. Let me try to see what mistake I am doing here. Did I do this multiplication correctly? So I have minus 2. I didn't do this correctly. Okay. So I have here minus 2 in this one, and in the next one I would have 8 minus 5. And this is 3. I have already done that calculation here. And the second row is correct. Now let me try to do this calculation once more. So I would have here minus 2 and 1 here. And this is going to be minus 4 plus 3 is minus 1. And this is 4 and minus 4. Is this also wrong? Let me see. 2 minus 4 is minus 2. Okay, sorry for this. So I have my new matrix A bar given like that. Okay? So now I can actually write you the general case. So that A bar matrix is not really an arbitrary matrix here, you see. Okay? The new A bar matrix that we have found is -2, 1, -1, and -2. Okay? So now this has a relationship with the eigenvalues. You see that when I look at the eigenvalues, the real part is -2, which are on the diagonal here, and their imaginary parts are here and here. Okay? So this is quite convenient. If the eigenvalues are in the following form, let me write here the general case. In the general case, if the eigenvalues are lambda 1 is equal to alpha plus j beta, and lambda 2 equals to alpha minus j beta, in that case, this A bar matrix is always going to turn out to be as follows. The real part of the eigenvalues, they should be the same, and the imaginary part of lambda 1 is going to be here, and the imaginary part of the other one is going to be here. Okay? Now I can actually talk about why this is the case. Why this should be the case for a general A matrix. Let me try to explain this. We have used this type of argument here in the previous lecture. Now let me try to do this. I know that A bar is in general equal to P inverse AP. This is our general formula. And in the last lecture, I have actually told you that we always use this equation in the following form. P times A bar is equal to A times P. Okay? Now what I would like to do is to use this equation to show that when I choose my P in this form, then A bar is always going to be in this form. Okay? So let me try to show it. So here I'm selecting my P, this specifically as the real part of the first eigenvector and the imaginary part of the first eigenvector. Okay? And I know that these eigenvectors are satisfying the following relationship. I know that this eigenvector satisfies this relationship. A times E1 is equal to lambda 1 times E1. Okay? And that actually means that, so E1 is composed of its real part and its imaginary part. So E1 can be written as real E1 plus J imaginary E1. Okay? That is what E1 is. So now let us use this equation to show that A bar is going to be in this form. So I will write P first. P is going to be this matrix, real E1 and imaginary E1. These are the columns of the P matrix. A bar is what I would like to find here, is equal to A times P again, real E1 and imaginary E1. Okay? Here we know that I can do this multiplication using the partition matrix multiplication rules. This is nothing but A times real part of E1, this vector times A, and the second column is going to be A times the imaginary part of E1. Okay? So here, in order to be able to find the first column of A bar, this is my A bar, I need to express this vector, this first column here, as a linear combination of this vector and this vector. Then the coefficients are going to be my A bar first column elements. And remember in the last lecture, I called this as A11 bar. Maybe bar is not a good notation now. I will just call it A11, A21, A12 and A22. I don't use bar because I define bar to be complex conjugate there. It's not going to be a good notation anymore if I use it in that way. So that is my A bar matrix, and we know that such a multiplication would give me just this. A11 times, the first column is going to be A11 times this, A11 times real E1, plus A21 times the second column, imaginary E1. This is going to be my first column on the right-hand side, and the left-hand side, and the second column on the left-hand side is going to be A12 times real E1 plus A22 times imaginary E1. Okay? So now I see that the problem is express the first column as a linear combination of the columns here, and the coefficient of real E1 is going to be A11, coefficient of imaginary E1 is going to be A21. Okay? Express A times imaginary E1 as a linear combination of these columns, and the coefficient of the first column is going to be A12, coefficient of the second column is going to be A22. Okay? So now let us try to obtain these coefficients. And what should I use here in order to be able to obtain these coefficients? So here is what I should do. I have this eigenvector equation, AE1 is equal to lambda 1 E1. Okay? Now I will take the real part of both sides. Remember that this A matrix is just a real matrix. Okay? So I have real part of AE1 is going to be real part of lambda 1 E1. Okay? Now here you should be careful, because in this case real operator really cannot be distributed over multiplication. It can be only distributed over multiplication if one of the elements of the multiplication, one of the multiplicants, is actually real. Here, this is a complex number. This is a complex vector. Definitely, I cannot distribute the real operator here over this multiplication. But here, it is nice because A is always real. It has real elements, and E1 is complex. Since one of the multiplicants is actually real here, I can distribute this as this. Real of A, and I can actually write real of E1 here. Okay? Or here I really do not have to write real of A at all. I can take it outside directly. So this is A times real part of E1. And here I cannot do that distributing because both of the elements are complex here. So then what to do here on the right hand side? So it is simple. Instead of lambda 1, I write alpha plus j beta. And instead of E1, I write real of E1 plus j imaginary of E1. Real E1, and I have imaginary E1. Okay? So then I need to calculate the real part of this multiplication. But it is easy to calculate the real part because the real part is going to be these two multiplicants here, multiplied, alpha times real E1, plus these two imaginary parts, j squared is going to be minus 1, and I have beta imaginary E1. Okay, so I have A times real E1 is alpha times real E1 minus beta times imaginary E1. So here we see that if I had this thing like this, then real E1, our first vector, would be an eigenvector. But you see that I need to add a non-zero vector here. So real E1 is not really an eigenvector anymore. So here, what does this tell me? This tells me that A times real E1 is alpha times real E1 minus beta times imaginary E1. That tells me that A11 is alpha and A21 is minus beta. Okay? This is the first column of A bar, and then I need to obtain also the second column. Okay? How do I obtain the second column? For the second column, I need to express A times imaginary E1 as a linear combination of real E1 and imaginary E1. And the coefficients would give me the second column elements. So I will now, what I'm going to do is just to, instead of the real part of this equation, calculate the imaginary part of this equation. A times E1, imaginary part, is equal to imaginary of lambda 1 E1. Okay? Now, this A, because it's real, it can be taken outside. A times imaginary E1 is equal to, this is going to be imaginary part of the eigenvalue alpha plus j beta times the eigenvector real E1 plus j imaginary E1. Okay? And in the overall, I need to take the imaginary part of this multiplication here. And we see that the imaginary part is easily given by beta times real E1 plus alpha times imaginary E1. And this is A times imaginary E1. So we see here that this coefficient A12 has to be beta, and coefficient A22 has to be alpha. Okay? So we see that if I find the first eigenvector, if I first find the first complex eigenvalue, then if I find the first complex eigenvector, then when I change my coordinates into real and imaginary parts of that eigenvector, then the new A matrix that I obtain this is the A matrix for the Z coordinates here. The new A matrix A bar turns out to be in this interesting form. Okay? So let me try to write our results here. So I have Z dot is equal to A bar times Z, and Z dot is therefore equal to, I have minus 2, 1, and minus 1 times Z. Okay? And this is the case for the general case. So I have lambda 1 equals to alpha plus j beta, and lambda 2 equals to alpha minus j beta. In that case, I would have the system alpha beta minus beta z. This is the general case. This is the specific case that we have obtained. Okay? Remember the real eigenvalue case. In the real eigenvalue case, this A bar was really simple. It was diagonal and it was decoupling the components of Z. Dynamics of the components of Z were decoupled. But here I see that there is still no decoupling. Okay? So I see that the differential equation for Z1 would still depend on that of Z2. So the value of Z2. So I have Z1 dot is equal to, if I write the differential equations corresponding to this equation, then that is going to give me Z1 dot is equal to minus 2Z1 plus Z2. and Z2 dot is equal to minus 1 Z1 minus 2 Z2. So you see that there is still no decoupling. So this really looks bad at this point, because in the real case we could decouple the equations and we could solve them individually, first order differential equations, and we use that result to obtain the trajectories in the z plane. Okay? But here there seems to be no decoupling. Why is that? Because in this rotational motion, you cannot really choose real vectors as your new coordinates, which are real part. And whatever real vectors you select here, you can never decouple those Z1 and Z2 modes from each other. Okay? Unfortunately, this is not possible to do by choosing any real coordinate vectors here. When is it possible? If instead I put E1 and E2 here, eigenvectors, then I could decouple these two modes. But in that case, these coefficients of A bar would be complex variables, okay? Which we do not want to deal with here. So what are we going to do here afterwards? This was the first coordinate change. So unfortunately, in order to be able to continue after this point, in order to be able to visualize the trajectories in the z plane, we will need to make one more coordinate change. And that coordinate change after this point is going to be a coordinate change into a coordinate system where oscillations would look much better. We are going to go into another coordinate system where the oscillations would look much better than the Cartesian coordinate system like Z1 and Z2 here. And that coordinate system, as you might guess here, is going to be polar coordinates. Okay? So we have changed first into this new coordinate system, but still the modes are not decoupled from each other. And now, in order to be able to do that type of decoupling, we're going to go into a coordinate system where oscillations would look much better than than they look in the Cartesian coordinate system. And this new coordinate system is going to be the polar coordinates. Okay? So this is going to be just a second coordinate change on the same system. That is why the investigation of the complex case is usually much more difficult. At least analytical investigation like this. In practice, we really do not calculate these new coordinates at all. And here, in order to be able to explain this topic in detail, I needed to show you all of these details. So here is what I would like to do. We had the original coordinate system here, x1 and x2, and I have defined my new coordinate vectors. So this was what Z1 was looking, and Z2 was the same axis. It had the same axis as x2. Okay, this is my new axis, and this is the second new axis. And we have shown that in this new coordinate system, our complex system, x dot is equal to ax, looks a little bit simpler than the original one. Okay? On the real elements of A bar, I have the real part of the eigenvalues, and on the off-diagonal elements of I have the real part of the eigenvalues, and in the off-diagonal elements, I have the imaginary parts. Okay? So now I'm going to try to visualize the motion of the system in the Z1, Z2 plane. But still, I told you that since those equations are not decoupled, it is difficult to visualize, make that visualization in that plane either. So here is what I'm going to do. I'm going to go into the new variables r and theta, which is nothing but the polar coordinates in the z plane. So I have the r as this distance, and I have the theta here from the positive z1 axis. Okay? Any z1, any vector z1, z2 can be written in terms of its coordinates r and theta in this axis, in the polar coordinates. So here is our variables. Z1 is equal to r cosine theta, and Z2 is r sine theta. Of course, you know the inverse transformation as well. So r is nothing but square root of Z1 square plus Z2 square, and theta is nothing but arctangent Z2 over Z1. But here we are not going to be using the inverse relationships at all. So then how can I change my state variables Z1 and Z2 into r and theta? So what should be our aim? Here, our aim, remember when we went from x to z, what we did was, here I had the equation of this type. X dot is equal to ax. When I went into this, this was my transformation. X or z equals to P inverse times x. Then we obtained a new state equation. Z dot is equal to, I have a bar times z. Okay. Now we are going to go into a new state variables here, and these state variables would be r and theta. We will want the same thing. I want to obtain the system dynamics in these new coordinates. In these new coordinates, I want to find two functions, two equations. The first equation is going to be the dynamics of r, and the second equation is going to be the dynamics of theta. Okay? So I would like to obtain such two equations after I change the coordinates into r and theta. Okay? So now let us try to do this. I will now calculate Z1 dot. But here you need to be careful because the right hand side is dependent on r and theta. So if I take any function g of r and theta, and if I take its derivative with respect to time, you see that the function does not depend on time explicitly, but it depends on time implicitly because r and theta are dependent on time. Okay? So here is what I do. This is going to be del g over del r first, and del r over del t, plus del g over del theta, and del theta over del t. Okay? I think you know such a rule from your calculus courses. And this is nothing but r dot, and this is nothing but theta dot. Okay? So we have del g over del r times r dot plus del g over del theta times theta dot. Okay? So now let us calculate Z1 dot. Z1 dot is equal to, this is a function of r and theta, and I will first take the derivative with respect to r, cosine theta times r dot, plus derivative with respect to theta, and I would have minus r sine theta times theta dot. Okay? So this is what Z1 dot is. All right? In terms of r dot and theta dot. Now what I would like to do is to use this equation that I have obtained as well. So it is, as you see, it says that z1 dot is at the same time equal to minus 2z1 plus z2. So this thing should be equal to minus 2 times z1. z1 is r cosine theta plus z2. z2 is r sine theta. Okay? So I get here an equation for z1 dot, and you see that these two quantities should be equal if I did everything correctly. Okay? Let us calculate z2 dot is equal to derivative of this thing with respect to r. It is sine theta times r dot. And derivative of this thing with respect to theta, it is r cosine theta times, let me put this here, and I have theta dot. Okay? Then I'm going to use my system dynamics, this one, minus 1 times z1. z1 is r cosine theta, and I have minus 2 z2. z2 is r sine theta. Okay? So now I got two equations that I can use to obtain equations of this form. R dot is equal to G1 r theta, and theta dot is equal to G2 r theta. These are the dynamics in the r and theta coordinates. Okay? And in general, these can turn out to be nonlinear for a general system in Z. But here we see that for a system of this form, this form that is in the new coordinate, the equations that we are going to find are really going to be simple. And furthermore, the equations for r and theta will be decoupled. Okay? So we couldn't decouple the equations in the new coordinates z1 and z2, but due to the simple form of the A bar matrix here, we could decouple the variables in polar coordinates, r and theta. So here is what I'm going to do. I'm going to erase this part, and I'm going to use these equations in order to extract first r dot and to extract theta dot then. Okay? I want to extract r dot from these two equations. I want to write r dot without any derivatives on the right hand side. Okay? So you see that in these state equations, you can never have r dot or theta dot on the right. So the right hand side should always contain these variables, coordinate variables, without any derivatives. The left hand side is r dot and theta dot. So I have two equations, r dot, and I have two variables to extract, r dot and theta dot. Okay? And from these two equations, I can express these r dot and theta dot variables in terms of non-dotted variables. Okay? Variables without any derivatives. So how do I do this? So it is really difficult or it is not difficult, but it is tedious to actually try to solve these two equations for r dot and theta dot. Instead, I'm going to do an equivalent thing, but it is going to be just less tedious than trying to solve these equations at the same time. So here is what I'm going to do. I'm going to try to obtain what r dot is. And I'm going to do this by multiplying the first equation with some variable, both sides, and I will multiply the second equation with another variable, and then I will sum. If I would like to calculate r dot from these two equations, I can use the relationship cosine square plus sine square is equal to 1. So I will first multiply both sides of the first equation with cosine theta, and then I will sum by multiplying both sides of the second equation with sine theta. In that case, you see that I will get r dot times cosine square plus r dot times sine square. When I sum these equations, I would just get r dot. Okay? So the first term is r dot. What about the second term? Multiply this term with cosine plus multiply this term with sine and then sum. You see that you're going to get 0. Okay? That is equal to multiply this term with cosine and multiply this term with sine. And then sum. You get minus 2r. Cosine square plus sine square is 1. And multiply this term. I can put 1 here as well. Okay? Multiply this term with cosine and multiply this term with sine. And then sum, you would get 0. So this is my first equation. You see that I have written r dot in terms of a function of r and theta. But you see that the right-hand side doesn't depend on theta anymore. So you see that the r equation in the polar coordinates is decoupled from the theta equation. Okay? So now let us do the same thing for theta. Here I really do not want to write these equations over and over, so I'm actually making my change like this. So now here is what I would like to do. I would like to obtain theta dot from these equations, and in order to be able to do that, I will do the similar thing. So I want here sine square. Let us say plus sine square. So I will multiply the first equation with minus sine theta. And I will multiply the second equation with cosine theta. And then I will sum. Okay? If I do that, you see that the summation of these two terms after the multiplication would be 0. And summation of these terms would be r times theta dot. Okay? Because I have a common term here, r. Sine square plus cosine square would be summed. It's going to be 1, and I have theta dot. That is equal to... Now you see that here I have, in the earlier case, these terms gave me my result, and these terms were cancelled. Here now I would like to, I see that here, in this case, these terms are going to cancel each other, because this is going to be multiplied with minus sine theta, and this is going to be multiplied with cosine theta, and I will sum them, they would give me 0. Okay? But these terms are not like that. When multiplied with minus sine theta, these are going to give me minus r sine square, and this is going to give me minus r cosine square. When I sum them, it's going to give me minus r. And when I look at this equation, if I assume that if r is not equal to 0, because r equals to 0 is just a single point here, okay? And I know that this point is going to be an equilibrium point. I really do not need to obtain the dynamics at that point. At that point, everything is going to be equal, all the derivatives will be equal to 0, and the system will remain there. Okay? So here, the equilibrium point of the original system is here. How do I know if both of the eigenvalues are equal to 0? We would get the real eigenvalue case. Okay? And in the complex eigenvalue case, if the real and in the complex eigenvalue case, I need to have the imaginary parts non-zero, okay? Because otherwise, I would obtain the real eigenvalue case, okay? Since the imaginary parts are non-zero, and I have alpha minus j plus j beta, alpha minus j beta, I see that none of the eigenvalues are actually equal to 0. That means that in the complex eigenvalue case, when the imaginary parts of the eigenvalues are non-zero, we are always going to have an invertible A matrix, because the determinant is always going to be non-zero. Okay? That means that the original system has a single isolated equilibrium point at the origin, but since P is invertible, the Z system would also have a single isolated equilibrium point at the origin. And I know what the dynamics at the origin is. This point corresponds to R equals to 0, and this is an equilibrium point. So if the system is started at this point, it's going to remain forever at this point. So really I don't need to obtain the dynamics at the origin. So if I assume that R is not equal to 0, then I can cancel these R's here. Then that would give me theta dot is equal to -1. Okay? So this is my equation for theta. So you see that I have changed my coordinates into polar coordinates, and I have obtained the following equations. R dot is equal to -2R, and theta dot is equal to -1. Okay? So you see that in the polar coordinates, the dynamics equations of the system are actually decoupled from each other. So the radius variable is actually independent from the angle variable. Okay? I can actually solve these equations individually then. So let us solve this equation. It tells us that R of t is equal to e to the -2t times R0, the initial radius. And what about theta dot? If theta dot is equal to -1, I hope you know how to solve that type of basic differential equations. So this is d theta over dt is equal to -1. That means that d theta is equal to minus dt. Integrate both sides. Theta is equal to minus t plus c, the constant. But you see, if you substitute t equals to 0, you see that c should be equal to theta 0. That means that theta of t is going to be minus t plus theta 0. Okay? So we could solve both of the differential equations, and now I can try to visualize the motion in the Z1, Z2 plane using the polar coordinates. Okay? But before that, I would like to talk about the general case. So I have told you that the general case was looking like this. Okay? So at this point, if you have this general system, at that point, if you change your variables into polar coordinates, then what would you obtain? Here I will not be able to do this calculation because it requires the repetition of all of the calculations that I have done here for that general system. I would like you to do that yourself as an exercise. And at the end, you are going to see that if you do that conversion, so if you go into the polar coordinates, then you would obtain the following equations. R dot is equal to, I have alpha times R, okay? It is this equation. In this case, the real part of the eigenvalues was -2. That means that I have R dot is equal to alpha R, and theta dot in the general case is minus beta. Okay? So now let us look at the types of these equilibrium points. How can I classify the equilibrium points, that means the origin here, depending on the values of alpha and beta, the real part and the imaginary part of the eigenvalues. Maybe before going into the classification, I can go back to my specific case here. Okay? In my specific case, I had these equations. Okay? And what type of motion would that mean? First of all, I have theta dot is equal to -1. Okay? This means a constant angular velocity in the Z1, Z2 plane. So theta dot is going to be turning. So theta would be turning like this. So the state would be turning like this with constant angular velocity. And the angular velocity is -1. Okay? And what about the radius? So I know that theta would be rotating like this. But the clockwise or counterclockwise, I know that the angular velocity is negative. Okay? In the state space, the positive theta means counterclockwise rotation. Okay? Positive theta dot means counterclockwise rotation. And I see here that the angular velocity is negative. That means a clockwise rotation. So the angle of the state would be rotating with constant angular velocity. So state would be rotating like this. But what about the what about the radius? Is the radius going to get smaller and smaller, or is it going to get larger and larger like this, or it's going to remain constant? Is it going to remain constant? Which one would it be? So here we see the radius equation. I'm actually working with radar systems, and that is why sometimes I call this R as the range. Okay? It should be radius here in this course. This is not related to range at all. So it is a radius variable. So if I say range, you should convert it to radius in your mind. Okay? So I see here that since alpha is here negative, I have this initial radius always decreases because R of t is e to the -2t times the initial radius. That means that the radius is always going to get smaller and smaller, and it's going to converging to 0. It's going to converge to 0. Why is that? Because this exponentially is converging to 0. Okay? The radius is going to exponentially converge to 0, and the state is going to be converging to the origin. Okay? So we would have a rotation in clockwise direction, and the radius would be always decreasing. So if I am at this point at time t equals to 0, then my theta would be rotating like this. Okay, but the radius would be getting smaller and smaller. So this is going to be my new radius, so the distance to the origin is going to decrease, and similarly, as I rotate, this distance is going to get smaller and smaller. But that is actually telling me that the motion is going to be something like this. Okay, the radius is always going to get smaller and smaller. We would be rotating in that direction, and we're converging to 0. All right? In Z1, Z2 plane, the motion is looking like this. Okay? Then what about the motion in the original X1, X2 plane? Okay? So here Z1 and Z2 are like they are separated from each other just a little bit. I would actually pry this angle to a larger value, and I would put this space on top of this one. So in general, when I have a circle in Z1, Z2 plane, if I change the orientation of these axes and if I place it back into my original coordinates, these are going to turn into ellipses. Okay? So the motion in X1, X2 plane is going to be looking like this. Okay? So some ellipsoids in that case. I don't know. I actually could not. If I make some additional analysis, I could understand whether these ellipsoids are going to be like this or they're going to be like this. But here I don't want to deal with it. So just know that the circles in Z1, Z2 plane is going to look like ellipses in general. If Z1 and Z2 are different than X1 and X2, then these circles are going to turn into ellipsoids in the original X1, X2 plane. All right? So now we can actually try to classify these equilibrium points according to the signs of alpha and beta. Okay? So here you see that in the Z1, Z2 plane and in the X1, X2 plane, the trajectories around the equilibrium point, for this specific example, they are converging back to the equilibrium point. Okay? So would I call such a system or such an equilibrium point a stable equilibrium point or an unstable equilibrium point? So this would be a stable equilibrium point because all trajectories around the equilibrium point would always converge to the equilibrium point. In the later parts of this course, when we investigate the stability of systems, we are going to define rigorously what stability means for an equilibrium point. Okay? Currently, we just have to continue with an intuitive notion of stability. Okay? So, but later we are going to define stability in much more detail, and we are going to see the characteristics around equilibrium points. We are going to classify equilibrium points as well when we try to cover the concept of stability. But this equilibrium point would be called a stable equilibrium point because all trajectories around it would converge to the equilibrium point, and we are going to call such behavior a focus type of behavior. So we are going to call that equilibrium point a stable focus. Okay? So now we can go into the types of equilibrium points. Types of equilibrium points. When the eigenvalues were real, we could classify the equilibrium points like node or saddle point, and in this case there are also two cases: focus and center. Okay, let us try to investigate these types. So the first type is alpha is larger than 0, let us say. Beta is larger than 0. So remember, this is our general case. Okay? Now I would like to investigate this type. This general expression. Now if beta, so I have my Z1, Z2 plane. Beta is positive, just like the case in the earlier example. And in the earlier example, beta was 1. And here I have, if beta is positive, then the angular velocity would be negative. That means that we have clockwise rotation. And what about the case when alpha is positive? If alpha is positive, then I would have r dot is equal to alpha r. And if alpha is positive, the argument of this exponential would be positive. I would have the solution for this case would be r of t is equal to e to the alpha t, r0, and theta of t is equal to minus beta t and plus theta 0. Okay? So if beta is positive, clockwise rotation. If alpha is positive, I would see that the radius is going to diverge to infinity. So if I start from here, I will rotate in the clockwise direction, just as our example, but the radius is going to get larger and larger. Okay? So we're going to get a divergence of this form, and this is going to be correct for any initial condition that I start from around the origin, except for the origin. If I start at the origin, I know that that is an equilibrium point, I will stay there. But if I start anywhere else, anywhere other than the origin, then the trajectories would be diverging towards infinity. So this type of equilibrium points are called unstable focus. Okay. Good, okay. And of course, you know what the second type is, our example. So alpha is smaller than 0. Let us say in this case beta is smaller than 0 as well. Okay? You know beta just determines the direction and the frequency of oscillation here. Alright? Beta just determines the direction and the frequency of oscillation. And you know that alpha determines whether the trajectories are approaching the equilibrium point or they are diverging from the equilibrium point. So this is just similar to the poles of a linear system that you have seen in the control course EE404. Okay? Remember, if the poles are in the left half plane, if this is my complex plane, okay? Real of S, imaginary of S, if poles are here in the left half plane, then their real part is negative. That means that we have a stable system. So here, in this case, we are looking at the eigenvalues of A. If they are in the left half plane, then the trajectories would be stable. And whether they are left in the left half plane or not is determined by alpha. If alpha is negative, then the trajectories would be converging to origin because the radius would be converging to origin by this equation if alpha is negative. Okay? If on the other hand, if alpha is positive, if the eigenvalues are in the right half plane, that means if I were looking at the poles of a linear system, if I had poles in the right half plane, then that would mean instability of the system. Okay? In that case, the trajectories would be diverging away from the equilibrium point. So there is an analogy with the, and actually if this system x dot is equal to ax, this system is an autonomous system. It doesn't have an input. Okay? Since it doesn't have an input, I cannot talk about the poles or zeros of this system, because poles and zeros of the system are related to the transfer function. Okay? And transfer function is an input-output descriptor for a linear system. Here in this system, I don't really have any input. So I cannot talk about its transfer function when the input is not defined. But I know that if I define an input to the system, then the poles of the system would be the eigenvalues of A. Okay? You have seen this in, I hope you remember them. You have seen this type of concept at the end of 302. When you have a state space system with an input, if you look at the poles, they turn out to be the eigenvalues of A. So here, without the input, I cannot talk about poles of the system. That is why we are talking about only the eigenvalues of the system. But if the system had an input, then I could talk about the transfer function and the poles of a system. And poles of the system would be the same as the eigenvalues of the system, of the matrix A. Okay? So in this case, if alpha is smaller than 0, and if beta is smaller than 0. If beta is smaller than 0, then theta dot is going to be positive. That means counterclockwise rotation in the Z1, Z2 plane. And I see that alpha is smaller than 0. Radius is going to be getting smaller and smaller. So the system trajectories in the Z1, Z2 plane would be looking like this. This is called a stable focus. Okay? And our example was also a stable focus. Okay, this is the same. Just the direction of rotation changes. Let us now look at a third case. Alpha is smaller than 0, beta is equal to 0. This is a tricky question actually. So what would be the trajectories looking like. In this case, theta dot is equal to 0, okay? That means that we are not going to have any rotation at all, because the angular velocity is 0 here, all right? And alpha is smaller than 0, which means that the radius is going to get smaller and smaller. So when I have Z1, Z2 plane like this, if I start a trajectory from here, its theta is not going to change. Beta is 0, that means that theta of t is theta 0, okay? But the radius is going to get smaller and smaller. So we are actually going on this line towards the origin, okay? So what is the name of this type of equilibrium point in that case? It is stable focus. It is not. So here, why is it not? Because this is not a case with complex eigenvalues at all. The complexity, the complexness of the eigenvalues are determined by beta. If beta is non-zero, then alpha plus j beta and alpha minus j beta, they are complex. Okay? So, but here, if beta is equal to 0, then none of the eigenvalues are complex. We go back to the real eigenvalue case. Real and equal eigenvalue case in this case. So in this case, this equilibrium point is nothing but a node, and it's nothing but a stable node. Okay? So remember, if beta is equal to 0, we get out of the case of complex eigenvalues, and we go back to the case of real eigenvalues, which are equal to each other. And that is nothing but the stable node case. All right? So this was a tricky question. So finally, let us try to see the case when alpha is equal to 0, but beta is either larger or smaller than 0. So I have the fourth case, alpha equals to 0, beta, let us say it is smaller than 0. Beta smaller than 0 means counterclockwise rotation, and that means that, oh, this is not good. Z1 and Z2 here. So we're going to rotate in counterclockwise direction. But what about the radius? In this case, we see that alpha t is going to be just equal to 0. That means that e to the 0 is going to be 1, so the radius is always going to be equal to the initial radius. Okay? So the radius will not change, but we are going to rotate, okay, in the counterclockwise direction. So we have trajectories just like circles, like this. So radius is not going to decrease, is not going to increase either. Okay? In that case, this equilibrium point is called a center. Okay? And we generally do not talk about the stability or instability of a center. It is like a critically stable system, because the eigenvalues are exactly on the imaginary axis. Okay? So when you have a center, in general, what would be the period of this oscillation? So I can talk about the frequency of oscillation, f. I can talk about the period of oscillation, t. Okay? What do you think the period of oscillation would be? So here we are given theta dot, okay? And this theta dot is nothing but minus beta, okay? And in general, theta dot is nothing but the angular velocity omega, all right? So I have the angular velocity omega. This is 2 pi f, okay? It is minus pi. Then the frequency of oscillations would be just minus beta over 2 pi, okay? And what about the period of oscillation? It is the reverse of this thing. But I want generally a period of oscillation which is positive. So frequency, we talk about negative frequency always in Fourier transform, etc. So negative frequency can make some sense, but I really do not want to work with negative period of oscillation. So instead I can just write this. 2 pi over absolute value of beta would give you the period of oscillation. It is similarly here for focuses you can define a frequency. How can you define a frequency? You define an angle and you look at the frequency at which the trajectory hits this line at a constant angle. That would give us the same period and the same frequency here. Okay? So in general, the frequency of oscillation we talk about is beta over 2 pi, or you can talk about the period of oscillation, it's 2 pi over beta. Okay? So here this completes all the cases. I have stable, unstable focus, or I have a center type. This case is not belonging to the complex eigenvalue case at all, and we call this case a stable node. So that completes this lecture of the investigation of the complex case. In the future lectures, when we go into the eigenvalues, when we go into nonlinear systems and the investigation of phase plane trajectories around equilibrium points of nonlinear systems, we are going to look at these eigenvalues of the A matrices of linearized systems, and we are going to try to decide on these trajectories around the equilibrium points by using this linear system theory. But this actually completes this lecture, investigation of the complex eigenvalue case, and in the next lecture we are going to solve an example, and we are going to first try to summarize the theory that we have seen so far. But that's all for this lecture. Thank you very much for watching. Bye.